Okay, today we'll move on to our next group presentation, which is group number 2. So we're going to listen to a presentation on JFET, right? So for group number 2, we have Dayang, we have Darwina, Fatin, and Go, and finally Ifa. Okay, so is everyone around already? Who's your group leader, by the way? Dayang, right? Dayang, is everyone around already in your team?
Yes, already.
Right, can you turn on your videos, your cameras? Okay. All right, good. So it's the first time me looking at few faces here. So I've seen Go. Go is my team for FYP. So Dayang, Terwina, okay. Ifa, all right. So Ifa dengan siapa tu? Dengan your team member lah. Together, right? Fatin ke? Okay, all right. Okay then. Okay, all right then. Okay, you're sharing together. Okay, so the floor is yours. Go ahead. You can share your screen and start right away. Let's welcome group number 2. Okay, looking good. Go ahead.
Can we start now, Doctor?
Yes, you may start now.
Assalamualaikum and good morning to our dedicated doctor and our fellow friends. My name is Fatin Tahira. We will conduct the presentation, and our group 2, which leads by Dayang Hamiza binti Alin, Darwina Alina binti Akbar, me myself Fatin, Go Zon Keng, and Ifa Farzana binti Zaidi. And our group will present about JFET, which is Junction Gate Field Effect Transistor. So in our presentation, we will talk about introduction, which is represented by me. And then we move on to device configuration, which we present by Daya. And then operating principle by Ken and Ifa. And lastly, we will talk about application by Derek. Okay, our group will focus on JFET, which is a junction gate field effect, which a voltage control device, which is essential for precision level voltage operated in analog electronics. What is analog electronic? It is a combination of analog machines and analog media, which is have the ability to record, measure, reproduce, and broadcast continuous info. Example is like record tape and also record player. And we proceed to JFET, which has 3 gate terminals. J is for gate, D is for drain, and S is for source. It can also be used as a switch and even can be made as an amplifier. So JFET has 2 types, which is N-channel JFET and also P-channel JFET. How we distinguish between these two is by seeing the arrow at the gate. If the arrow is pointed to the source, it is N-channel JFET and the gate voltage is negative. And if it's R Otherwise, if the arrow is pointing away from the source, it is P-channel JFET and the gate voltage is positive. The arrow also indicates the polarity of PN junction, which is formed between the channel and the gate. The current flowing through the drain and the source is dependable on the voltage applied to the gate terminal. The current does not have to cross through a PN junction on its way between source and drain because the path, which is called as a channel, is an uninterrupted block of semiconductor material. And the only practical difference between N and P channel is the biasing of PN junction formed between the gate material and the channel. Next, before we dive deep into JFET, I will simply brief you about JFET manufacturers in Malaysia. In fact, there are a few JFET manufacturers in Malaysia. For example, Mauser Electronic and Element 14. As you can see in the image included beside that, I use Mauser Electronic as reference because Mauser Electronic is quite near to us. It is located in Gelugo at Lebo to Pakhuruddin, and it is also an authorized distributor for many JFET manufacturers such as Fairchild, On Semiconductor, Vishay, and more. And as for their website, I will show it on the next slide. This is the example of their website. We can choose to modify a transistor according to our preference because there are so many categories they included. And the down below is the example for many types of different transistors. We can also purchase from them through their website. That's all for introduction. And as for device configuration, it will be presented by Dayang.
Okay, I am Dayang Hamiza binti Ahlib, so I'm to present on device configuration. Okay, for construction of JFET. A JFET consists of a P-type or N-type silicon bar containing two types of depletion layer at the sides. The bar forms the conducting channel for the charge carriers. The N channel consists of P-type material in N-type substrate, which is shown at the second picture, whereas P channel consists of N-type material in P-type substrate, which is from the first picture. From this picture, the purple color indicates the N-type and the blue color indicates the P-type. JFET is constructed using a long channel of semiconductor material. If the JFET contains great number of positive charge carriers, which is holes, it is a P-type JFET. While if the JFET contains large number of negative charge carriers, which is electrons, it is a N-type JFET. In the long channel of semiconductor material, ohmic contacts at each end are created to form the source and drain connections, which is at the above and the below one. A PN junction is formed in either one or both sides of the channel. Next. For JFET polarities, based from these pictures, in each case, the voltage between the gate and source is such that the gate is reverse biased. For example, from the N-channel JFET picture here, the negative of voltage of gate source is connected to the P-type at the gate junction. So that's why it is reverse bias. The source and drain terminals, which is at the above and the below one, are interchangeable. The input circuit, for example, here we take for gate to source of the JFET, is reverse bias, as I said before, which means that the device has high input impedance. The drain is so biased with respect to source that making the drain current flows from the source to drain, which means the current flowing upwards. In all JFETs, usually source current will be equal to the drain current. Next. Okay, for operating principle, will be presented by Ken.
Very good morning to all of you. I'm Junction. Now I would like to talk about the working principle of junction field effect transistor, or we call it JFET. For the JFET transistor diagram, there is a channel. We can differentiate it by looking at the polarity of the gate, terminal, and the channel. We can also see this JFET containing four important components. There is P gates, trans, and channel and source. Each of them play important roles in controlling the current flow in channel. So, how JFET controls the flow of current in the channel? For the first diagram A, the VDS and VGS is zero. There is no external current flowing through the JFET, so the depletion layer is the thinnest. The VDS is the voltage between drain terminal and source terminal, and VGS is the voltage between the gate terminal and the source terminal. For the second diagram, the VDS is positive voltage and VGS is negative voltage. This means that the reverse bias is applied in the gate, which can increase the thickness of depletion layers and squeezing the channel more smaller until the channel becomes so small that the current cannot pass through it. In these cases, it's called pinch off. The current is fully blocked by the depletion layers. For the last diagram C, the VDS is positive voltage and VGS is zero. There is no reverse voltage applied on the gate. So in this case, the JFET behave like normal conductor material. From these three diagrams, we can see that the operation of JFET is electric fields that generated by the input gates. Later, I will explain more about the working principle in following slides. Next. The left picture is belong to the N-channel JFET. From this picture, we can see this JFET consists of three legs corresponding to source, gate, and drains. JFET can also be categorized to two types that are N-channel JFET and P-channel JFET. We know that the channel is resistive in nature. A voltage gradient it does form down the length of the channel with this voltage become less positive as we go from the drain terminal to the source terminal. This makes the PN junction have a high reverse bias at the drain terminal and lower reverse bias as at the source terminal. Next slide. As I mentioned just now, from the both diagrams, we can see that the depletion layer, the depletion region is more thicker at the terminal compared with the source terminal. The working principle for the P-channel JFET is the same with N-channel JFET, but with different channel polarities, and the polarities of the bias voltage need to be reversed. So here I'm taking the N-channel JFET as our reference for explaining the JFET working principle. For the first diagrams, we can see that the switch is open. The VDS is applied between the drain and the source terminal, and VGS is zero. In this case, we can also call it as open channel. The two PN junctions at both sides establish the depletion layers. These depletion layers will always exist, even not connected to any external power source, due to the diffusion of electrons and holes to lower respective density zones to achieve equilibrium. The electrons for this case can flow freely from the source to drains through a channel between the depletion layers. Hence, when the switch is open, it causes a lower reverse bias at the PN junction and result in smaller depletion layers. This makes the maximum saturation current as DSS can flow through the channel. For the second diagram, the switch is closed, which is applied to the JFET, increase the reverse bias and create more thicker depletion layers at both sides PN junctions. This potential barrier restricts the current flow through the channel, hence the of the channel increase. If the reverse bias is further increased, The width of the channel decreases until no more current flows between the drains and the source. The JFET now is pins off like cut-off region for BJT. Pins off voltage VP is the voltage at which the channel is crossed. Next. Furthermore, I would like to explain the characteristics of voltage against current curve of channel JFETs. From this graph, it consists of many regions for describing the characteristic of JFET at certain value of VDS. When increase the reverse bias voltage, the current decrease until the pins off regions. The IDSS is the maximum saturation current and VP is the pins off voltage. The only region is the depression layers of the channel is very small when VGS is equal to 0. The pins off region or cut off region is when VDS is sufficient to cause the channel resistance to maximum and block the current flowing through the channel. Saturation or active region is the JFET become a good conductor. The value of VDS at this region does less effect on current flowing through the channel. The breakdown region is the region when the VDS is too high to cause the JFET's resistive channel to break down and pass uncontrolled maximum currents. For this region, the JFET is no longer working on controlling the current. The JFET is now defect. For the graph, you can see the knee is also known as knee voltage. It is the forward voltage at which the flow of current through the PN junction and also the boundary between omit and active regions. So how does the P-channel characteristic curve look like? Next slide. Okay, from these two graphs, we can see that the characteristic curve for the P-channel JFETs are the same with N-channel JFETs, except the drain current ID decrease with an increasing positive VGS. The polarity of the bias voltage, VGS and VDS is reversed compared with N-channel JFETs. Next slide. For the characteristics of the curve, we can actually attempt the value of ADSS, the maximum saturation current, VGS, VP, and VDS. From these four parameters, we can substitute them inside these two equations to calculate the drain currents, drain source channel resistance, and transconductance. That's all for my presentation. Thank you.
My name is Sifa. So in this part, we will have a look at the different biasing method used for JFET and their relative parameters. Okay, so for biasing JFET, there are different types of techniques that are used to bias the JFET in a proper manner. So from the various techniques, there are three that are widely used, which is fixed DC biasing technique, self-biasing technique, and potential divider biasing. So for self-biasing technique, it is the most common type of biasing method for during operation of JFET to get source junction remain reverse bias condition always. Notice there is no voltage applied to the gate. Vg is equal to 0 volt. For this state, the VGS voltage should be negative for N-channel JFET and positive for P-channel JFET to keep the junction reverse bias. By using a source resistor to have reverse bias JFET. The gate is returned to ground via RG and RS has been added to the source circuit. So in self here is added from VGS to bias the voltage. In this technique, the gate current is 0 again. The source voltage is determined by the same Ohm's law, which is V equal to IR. Therefore, the source voltage is equal to drain current times source resistor. So now the gate to source voltage can be determined by the difference between gate voltage and source voltage. Since the gate voltage is 0, as the gate current flow is 0 and the V equal to IR, gate voltage is equal to gate current and gate resistor is equal to 0. So the VGS is equal to 0 minus gate current times source resistance. Thus, there is no external biasing source is needed. The biasing is created by itself using the voltage drop across source resistor. So this voltage can be determined by using the formulas below. Okay. So for potential divider biasing, voltage divider bias can also be used to bias the JFET. In this technique, an additional resistor is used and the circuit is slightly modified from the self-biasing technique. A potential voltage divider using R1 and R2 provide the required DC biasing for the JFET. The voltage drop across the source resistor is needed to be larger than the resistor divider gate voltage. In such a way, the VGS remain negative. So this is how the JFET is constructed and biased. So to determine the VGS for a JFET voltage divider circuit with given VT, it can be calculated with the formulas below. Okay, lastly, for the fixed DC biasing technique, the current source bias is a used to increase bias junction field effect transistor through making ID independence on the VGS. It can be formed by connecting constant current source in series with the source of junction field effect transistor. It is shown in the below figure. So, in this circuit, BJT acts as a constant current source because its emitter current is essentially constant if VEE is larger than VBE. So the FET can also be used as a constant current source. So the advantages of this circuit is that it can provide the most stable key point value of ID. But the disadvantage of this biasing technique is that the circuit complexity can make it undesirable for most applications. So that's all about the JFET biasing method. Next, for the application.
Assalamualaikum and good morning. My name is Devina Alani and I'll be talking about the applications of JFET. Okay. Wait. Okay. For applications, there are a lot of applications that we can be used for JFET. One of it are switch, oscillatory circuits, buffer, digital circuits, amplifier, cascade amplifiers, a constant current source, and also a phase shift oscillator. But I'll be more focused on three applications, which is the common source amplifier, the constant current source, and also phase shift oscillator. Next. Okay. Well, firstly, for the amplifier, I'll be talking be more focusing on the common source JFET amplifier since it is a more basic design. Okay, the common source FET amplifier circuit is one of the most commonly used, which they provide current and voltage gain along with a satisfactory input and output impedance. The advantage for this amplifier is that it have a high input impedance and it also have a low noise output, which makes JFET ideal for use in amplifier circuits that have a very small input signals. But the disadvantages of this is that since JFET use depletion mode, they need to be always negatively biased. Okay, next. Okay, next is the constant current source. This constant current source and current sink. Current sink is the reverse for the constant current source. It is a simple way of forming biasing circuits, voltage references with a constant value of current. It is commonly used in capacitor charging circuits for accurate timing purposes or in rechargeable battery charging applications. In its simplest form, JFET can be used as a voltage control resistor where a small gate voltage controls the conduction of its channel. Okay, I didn't put the advantage and disadvantage for this. The advantage for this current constant source is that it is simple and it's also a cost effective, which means it is inexpensive. It is also more reliable and low noise. The disadvantage is that this constant current source may lead to power supply failure, and it also have a problem for its temperature coefficient. Okay, next. Okay, for last application is the phase shift oscillator, which the high input impedance of FET is very valuable in this application. A phase shift oscillator is a circuit that produces sine waves where the output is fed back to the input, which changes the phase of the waves. The phase shift will increase with frequency and can reach a maximum of 180 degrees, and it also can be used to generate signals over a wide frequency range that vary from a few Hz to 200 Hz by using one set of resistors with three capacitors ganged together to vary over a capacitance range in the 1:10 ratio. Similarly, the frequency ranges of 200 Hz to 2 kHz, 2 kHz to 20 kHz, and so on by using other set of resistor. The advantage of this application is that it provides a good frequency stability. It have a wide frequency range from a few Hz to several hundred kHz. It also suitable for low frequency, but the disadvantage is that the output is small due to the smaller feedback. It needs high voltage such as a 12-volt battery so as to develop sufficiently large feedback voltage. Okay. Next is the differences between JFET and BJT from group 1 yesterday. Okay, JFET is a unipolar device, but BJT is a bipolar device. The operation for JFET is that it depends on the control of a junction depletion width under reverse bias, and BJT will depend on the injection of magnetic carriers across a forward bias junction. Since JFET is a voltage-driven device, the current will go through the two terminals is controlled by a voltage at the gate. BJT is a current-driven device, which the current will go through the two terminals controlled by a current at the gate. JFET has a low noise level, but BJT have a high noise level. And JFET have a high input impedance, which is due to the reverse bias. And BJT have a low input impedance due to the forward bias. JFET also has a better thermal stability, and BJT have a less thermal stability. Okay, other advantages that I've already said in the application. This is more general advantage for JFET, which JFET have a very high input impedance, which will permit high degree of isolation between the input and output circuits. It also has a negative temperature coefficient of resistance, which can avoid the risk of thermal runaway. And JFET has a smaller size, longer life, and high efficiency, and also a majority charge carrier device, so it has a less noise. Okay, the disadvantage of JFET is that it's expensive and required to be handled carefully. It possesses a low voltage gains and small transconductance and a small gain bandwidth. Okay, I think that's all from us. Thank you.
All right, thank you, Group 2. So let's open Q&A session. Anyone? It's raining at my place, so it's a bit noisy. Boleh dengar bunyi hujan sekarang? Tak boleh dengar ada. It's a bit noisy around here. So any questions guys
Betul nak
on
tanya Dr.
JFET? Yes, go ahead. Faris kah?
Saya Rafai.
Ramai. Okay, right. Okay, go ahead.
Betul, sorry.
Tanya
Just
group
want to ask.
two. Don't ask
I
me.
just want. Okay, sorry. I just want to ask to the group two members. Is
Okay.
it the same concept between JFET and JFET and BJT in terms of its structure and also the operating principle?
Go ahead, group two.
I think not the same because for the JFET, it use the N channel, it use the channel to let the current to flow, but for the BJT, it use the PN junctions. For the JFET, we use the JFET is using the depletion layers to control the flow of currents, but I think BJT is not like this.
You might want to show the page just now, the last page where I think Darwina presented the difference between JFET and BJT. That's a very good slide. Can you go back to that slide and point to the differences? Yeah, this is a good slide. So yeah, where does it go that you mentioned just now, the operation principle and the device configuration, the difference between both? You mentioned something on this page, right? Go.
Yeah, the unipolar device for the JFET and the BJT is bipolar because the JFET is connected through only the N channels, but this to the P and N junction. P is the bipolar device.
Okay, anyone else would like to add on that? Ada? Okay, any other questions?
Me, Doctor. So I'm clear. So I'm going
Go
to
ahead.
ask, what happens if the thickness of the depletion layer decrease in the magnitude?
All right. Sorry, what happens when the thickness of the depletion layer is reduced? Is it?
Yes, reduce by the magnitude.
Okay, yeah. Okay, go ahead. Group two. Thickness of depletion layer is reduced. What's going to happen?
So if you decrease the depletion layers, we can use the depletion layers to control the flow of currents. If the depletion layer is decreased, the current there is more current can flow through the channels, as I mentioned before. If depletion layer is more thicker, we can see that the width of the channel is becomes so small to block the current from flowing. So if the thickness decrease, the maximum current can flow through.
Okay, so you have to control, you have to make sure that the depletion width is wide enough to cause pinch off, right?
Yes.
Else the current will still flow. Okay, that's okay, Ifa. Right. I have a question as well. Just now I think someone mentioned about Q point. I couldn't remember which one. Q point on the device. Was it Ifa or someone else? Can you explain a little bit about the Q point? What is Q point? Can you go to the slides of Q point? Yeah, it's on the slide. Biasing. What was it, Ifa? Ifa, right? So it's your name there. So what is Q point, Ifa? Is there any specific meaning of Q there? Oh, Ifa disconnected. Can you hear me?
Q is operating point.
Sorry, I couldn't hear clearly. Q what is what? Operating point. Is there any specific meaning of the Q there?
Question point.
What is Q there? Q point. What is Q? Is there any meaning of Q? Quality, I don't know. What Q is that? Can you find anything on Q?
It's a state. It is a steady state DC voltage.
Steady state. Provide the most stable Q point of value. Q point for ID, right? Steady state ID. So there's no specific term for the Q there.
Q.
I,
Question.
sorry?
Question point. Question point.
Oh, question point.
Yes.
All right, question point. So it's a stable point of operation.
Yes.
Okay, right. So is there any other question, guys?
Doctor,
Yeah.
my name is Nur Nabila.
Okay, go ahead, Nabila.
Dekat bahagian disadvantages tu, kenapa
Okay.
JFET negatively biased?
Okay, guys. Can you go to the page where you show disadvantages of JFET? I think among the last slides, right? Can you move on to the last slide, disadvantages, where you show about the negative bias. Ada lagi tak? Next slide. I couldn't recall which slide. Is it this slide or some other slide, Nabila?
Belakang sikit kot.
Can you move on to the next page? Is there any other?
I think it's on the amplifier disadvantage.
Right. Can you move on to that page? Amplifier page. Okay, where is it? Not here. Try to point at the slide. I couldn't remember the slide.
It's on the
Which one?
application.
Application, yeah.
Disadvantage.
Can you go? Okay, can you point to the
Application.
that particular slide? Application, yeah. Can you go there? I don't know which one.
Effectively biased. Wait a second.
Is it this one? No.
This
Oh,
one.
bukan
Yes,
kan?
yeah.
This one is it? Yeah. All right.
Yes.
Okay then. So yeah, the arena then.
Okay, because JFET is always negative bias relative to the source, but if it's happen to be, I think, positively biased, so that when it positive bias, the channel current will flow to the gate, not to source. Or in other words, I mean that the positive bias will cause increase in drain current, which will cause a failure on drain voltage and will cause the damage on the JFET itself.
Okay, so it's supposed to be negatively biased. But why is it so bad about negative bias? Because we say that as a disadvantage. It's not that bad, right? Is it so bad to negatively biased?
I think not.
All right. Okay. Is there any other question, guys?
Yes, I have a question.
Yeah, go ahead. Can you introduce yourself? Tell your name. I couldn't see on the screen right now.
My name is Hazwani.
Okay, Hazwani.
My question is, how JFET can turn into phase shift oscillator?
All right. Okay. How can it work as a phase shift oscillator?
Can you open the slide for the phase shift oscillator? Okay.
Can you move the slide to the phase shift? Phase shift oscillator just now. Okay, lagi.
Dengan
Okay.
sangkut.
Oh, sangkut.
Wait a
Alright. So
second.
okay, good. Right, it's good now. Okay.
Okay, phase shift oscillator. Okay, JFET, I think we know that it can have an amplifier action, right? But I think for this phase shift oscillator, I think it's called as a feedback action. So, which means, okay, as you can see on the second point, I already told that a phase shift oscillator is a circuit that produces sound waves where the output is fed back to the input, which changes the phase of the waves. So that means that the output on the last section is going to be supplied back to the gate with a phase shift happen between the amplifier output voltage and input voltage at the gate. Yeah.
So, talking about phase shift, does it have to be any specific phase shift angle or?
It can be any phase shift, but the maximum need to be until 180 degrees for one frequency only. The maximum.
So maximum 180 degrees and 180 degrees, yeah? Okay, I have one question. Since, well, we're now 10:43 already. We don't have time for another group, so let us finish with Q&A. Just now, I think Go showed the ID VDS, right? ID VDS curve. And there's a region called breakdown region. Can you go back to that page? What happens in the breakdown region where the VDS is high? ID VDS curve. This one, okay? Right. What's actually happening in the breakdown region? VDS is high, so what happens to the whole device? Go or anyone?
I think that the current, we can see that at the the current increase suddenly. So when at the breakdown, the JFET cannot control the current from flowing through the channel. So
Okay.
the JFET is no longer work the current controller.
Okay, so it's no longer working. Well, is something happening to your depletion region at this VDS value? Does it modulate the depletion region at this VDS value? Even though it's not controlled by the VDS in particular, right? But does it somehow affect the VDS, the depletion region? Because you put it down there, VDS too high to cause JFET resistive channel to break down and pass uncontrolled maximum current. Because well, you do pinch off when your VGS is high enough, right? The negative VGS is high enough, and then you get a pinch off. And then when the VDS is high, how does it alter the depletion width at all? Can it affect the depletion width?
I think the depletion layer will also break down.
Yeah.
maximum cut due to the too high currents flow through the channel, the VGS is too high.
So that means the depletion width is not only controlled by the VGS. So VGS also plays some role on the width because it
Yes.
affects the current anyway.
Yeah. Just like the limit of the JFETs for blocking the limit currents for flowing through the channel.
All right. So it's interesting to look into this because now what we see on the curve is the effect of the current control mechanism, right? And JFET is a voltage control device. You use voltage to control the channel conduction, you said. So going back to the physics, as I said last time, it's always related to the physics of the device. So we can see that at some point on the curve, the device is no longer working, or it can no longer modulate the current because it's now broken, if you like to say that. So that means it has to go back to the depletion width because that's how you control the channel conduction or the current flow. So try to try to understand, even though VGS is the one that's responsible for the depletion width control, how then the VDS interfere into the channel conduction mechanism, right? So that means at some point or at some level, at some extent, VDS also plays some role in controlling the current control, the voltage control mechanism in the device, because at some point it will break. Okay, try to look into that. So it's 10:48 already. So is there any last question, any burning question from you? Any last question from you? Hey, you cannot ask to me. You have to ask to group number 2 because this one is group presentation. You can write it down here. You can write it down here. We can discuss. They can answer first, and then we can discuss. Yeah. Unmute yourself and write down if you want to. Okay, come on. One last question. 10:48. Go ahead, Rafai.
Ni I don't know lah. This is question actually I'm focusing on you. But yeah, if they are the group 2 members can answer, yeah, it's good lah. So I just want to ask, okay, yesterday we talked about BJT and then BJT amplify the signal, and then the second one JFET also amplify. I'm not sure it is amplify what. So I just want to ask lah, what is the term of amplify mean? Does it amplify a signal only, or is just amplify volume or something else?
All right, group. What is amplifying? What is amplify? What does it amplify? Anyone? Saya nampak nama Darwina ni on the slide ni.
Signal.
Darwina punya soalan ni. Yeah, go ahead, Darwina.
I think it's amplify signal, but for BJT, I'm sorry. Yeah, for JFET, they can amplify like a small signal more than a BJT.
Okay, to relate to the amplification thing, what was the application of the amplification punya application yang we can see in real life? Contohlah kalau you're talking about amplify sound dekat speaker ke, for example, I don't know, turn on the volume or something that we can relate to. Where do we use this kind of amplifier, BJT, JFET, in the real products, for example? Apa kat mana kita amplify? What do we actually do to amplify?
Radio frequency.
Okay, so if you amplify radio frequency, then where do you use that radio frequency? what do we actually amplify? So ataupun BJT would like to add, BJT group 1, Amirul and team, kita amplify apa sebenarnya? Amplitude, okay, where is the amplitude that you want to amplify? Yes, we amplify amplitude in terms of current. Sekarang kita tengok collector current, base current, and everything. So when you amplify the current, what do you get? What do we get as a human? What do we get? What do we see as a result of the amplification process? Any of you would like to see? Okay, power. So where is the power that you get, the amplification? So the best is always to go to the product. Kat mana kita guna benda ni, then it's easier to relate to the amplification. Okay, dekat sini you can see the current and everything, right? And yesterday we talked about alpha amplification, gain, current gain and everything, right? So kita nak relate as a human, where do we see that? Any of you? Kita pakai kat mana? Any idea now?
Speaker, Doktor.
Okay, speaker. Kita pakai, kalau speaker kita pakai which one? Are you talking to JFET or BJT or a mix of both? Any idea? No idea for now. Okay, group 2. Nanti I nak you add few links, 1 or 2 links in the group, dalam WhatsApp group. Cuba bagi contoh that we can relate to as a person. Because all this stuff are in the device, in the products. Okay, kita tak nampak dia punya direct relationship lah. So, we want to appreciate the device, the semiconductor device in particular. So, we want to see volume ke, speaker ke, whatever. And how do we then relate the amplification in the JFET ke, BJT ke, to us as a human? Kita dengar louder sound ke, as a result of amplitude amplification, for example. Okay, can you give 1 or 2 links maybe in a group later on that we can read on further? Okay, right? So mungkin kadang-kadang sekarang pun yeah, maybe I don't know, microphone pun boleh juga. So try to see, kalau let's say kalau Arisha said microphone, so do we have BJT or JFET in a microphone? Do we have BJT or JFET in a speaker? Ataupun I don't know, radio ke whatever. So or we use both, or we use either one. And why is that? Is it due to the current level or voltage level or the mechanism behind the device operation? Okay. Okay, cuba explore on that. So this is the goal of the presentation. The moment you present, we ask question, we see new things, right? So these are the things that we can explore further. For example, katalah lepas ni you pergi interview company that works on BJT, which is doing amplification circuit, for example, for certain application. Then the application will be something that you can relate to right away. And the fundamental is in the amplification process of your device, okay? So it's going to be useful. So please insert a link or 2 in the group later on so that everyone can explore accordingly, okay? All right, so thank you very much, group 2. Wow, quite a long session, quite a number of questions. So it looks like now from 2 sessions per class, it looks like it becomes 1 session per class. So we're going to need like 2 weeks, which is week 12 and 13, I would think. And then I'm going to wrap up in week 14, and then we're going to be done. So thank you very much. Good work, good discussion. And let's give it up to group number 2. Virtually. Thank you very much. All right, thank you. Bye-bye. So, apa ni? Yeah, I cannot hear. Of course, but that's fine. Nanti Dayang, can you change the material into PDF and then email to me, yeah? Then I'll share as I shared group number 1's PDF like this morning. I already shared group number 1 slides on eLearn that you can take it on further. Okay, bye-bye. Take care. Assalamualaikum. So I'll see group number 3 next week already, because tomorrow is Friday. So next Wednesday, 1 p.m. as usual, group number 3 on photo detector. Bye-bye, take care, Assalamualaikum. Yeah, Monday, right? Esok dah Jumaat kan? Betul?
Yep.
And Monday, there's no public holiday, right? I usually miss public holidays, so
I'm not
so
sure.
Monday then.
I hope that
I
no.
don't. Yeah, I don't think so. Okay, so if nothing, if there's no public holiday, of course, Monday, 1 p.m. Group number 3. Bye bye. Take care.